my previous lecture, I have already told you about the Biot-Savart law, which says if a current carrying conductor contains a current I, then if this is dl0, then a vector r vector at a point P, then the magnetic field at the point P will be dB is equal to I dl0 cross r divided by r cube mu 0 by 4 pi. dl0 being in this direction, in the direction of current, and r being in this direction, dl0 cross r is rotating in this fashion, so the resultant vector is away from you. If the direction of current is reverted in this direction, then dl0 is in this direction, r is in this direction, screw is rotating in this fashion, so dl0 cross r going towards you. So this is the direction and magnitude of magnetic field at the point P, and this is Biot-Savart's law in nutshell. We are going to apply this Biot-Savart's law in case of finding magnetic field due to a current carrying conducting circular coil at a point on its axis, say P. The plane of the current carrying coil is something like that. The current is rotating in this fashion, say, then current is towards you at this point and current is away from you at this point. If we consider this semicircle, that is the half of the coil, then this is our L and this is our X and this is the point P. So dl0 cross L, dl0 is this element, current being in this direction, dl0 cross L, the angle between these two is 90 degree, because the plane containing dl0 and plane containing L, those two planes are at 90 degree. So dl0 cross L means dl0 L sin 90 degree. So actually dB at this point is equal to mu 0 by 4 pi I dl0 L sin 90 degree divided by L cube, that is mu 0 by 4 pi I dl0 by L square. Now what is the direction of this magnetic field? Cross product is a vector which is perpendicular to both dl0 and L, perpendicular to the plane containing dl0 and L. What is the plane containing dl0 and L? This is dl0, this is L, so the plane containing dl0 and L is this plane. So perpendicular to this plane means perpendicular to this hand, and perpendicular at this point is in this direction, perpendicular to at this point is in this direction. So if we place this is our PT, the vector dB, which is denoted as this. Now if we resolve this vector dB in two directions, one along horizontal direction, that is along x-axis, and another along perpendicular direction, perpendicular to the x-axis, then PV is dB cos theta and PH is dB sin theta. Now look, the current at this point is in this direction and current at this point is opposite direction. So the magnetic field is also at these two diametrically opposite points, one along this direction, other is along this direction. So if the component dB cos theta is in this direction, for this point the dB cos theta is opposite direction. So dB cos theta cancels out for the whole circle. So if we are considering all the diametrically opposite points, dB cos theta cancels out and we are left with dB sin theta. So magnetic field B is equal to integration dB sin theta. What is dB? Mu 0 by 4 pi I dl0. Sin theta means perpendicular by hypotenuse, A by L. So it is A by L. This is L square. We are left with mu 0 I 4 pi L cube A integration dl0. Mu 0 I A by 4 pi L cube all are constant and dl0 is to be integrated. Now this is a closed loop integral. closed loop integral. It is very important because when we are considering this point, we are also considering diametrically opposite point. So this is a closed loop integral, and closed loop integral dl is equal to 2 pi a. So we are left with mu 0 I 2 pi a square by 4 pi l cube. 2 pi, this gives 2. So this is mu 0 I a square by 2 l cube. So B equal to mu 0 I a square by 2 L cube means L square equal to x square plus a square. So this is x square plus a square whole to the power 3 by 2. If we are now considering a coil of n turns, closely packed n turns, then B is equal to mu 0 n I a square by 2 into x square plus a square whole to the power 3 by 2. If we require magnetic field at the center, then x equal to 0. B center equal to mu 0 n I a square divided by 2 a cube, giving mu 0 n I by 2a. Now what is the direction? I have already told you the resultant field is along x-axis. So here put an unit vector x cap, x cap, x cap, x cap. This is the magnetic field at the center, and this is the magnetic field at any point which is at a distance x from the center of the coil. So this is the magnetic field due to a circular coil carrying current I, and in the next lecture I will discuss some numericals which will help you to grasp the result of this formulae actually, and this formulae will be used in finding out the magnetic fields at different points, and those numericals I think will be helpful to you. Thank you.